This is Chemistry Hononegah High School, and this set of notes deals with the majority of Chapter 9, dealing with how do we draw molecules, molecular shapes, exceptions to our drawing rules, as well as molecule type and intermolecular force. First off, how do we draw molecules? There's actually a couple of different ways that we can represent molecules. You can see here a space-filling molecule for HCl, as well as what's called the Lewis electron dot, which is the form we'll be using. Now, when you go to draw simple molecules, the method we're going to be using really gives you a very important piece of information. It's designed to tell you the number of bonds, because if you know the number of bonds up front, it makes it significantly easier to draw the molecule. Multiple bonding situations are a whole lot easier if you know how many bonds you're supposed to have. Now, if the substance follows the octet rule, which is something we're going to be looking at today, an easy way to find the number of bonds is to use the N-A method. Remember, this only works if the substance follows the octet rule. Now, the rules we're going to use for drawing start with finding the number of bonds, and to do that we're going to use the N-A equals S method. Now, N would stand for the total number of electrons needed for all atoms in the structure to have a full octet, and remember, for most things that's going to be 8. The octet rule is you need 8 electrons, but for something like hydrogen, which its nearest noble gas is helium, that only needs 2. So hydrogen's octet would be 2 electrons. Everything else we look at, with few exceptions, will be 8. So really, when we're going to find out this for a substance like for SO3, set it up like this, because you know you're going to have things that need 8 and things that need 2. The question is how many of each. So the 8 would be how many non-hydrogens you have. Well, we have 1 sulfur and 3 oxygens. That's a total of 4 non-hydrogens, and since we have no hydrogens whatsoever, then this would be a 0. So what we have is basically 4 times 8, which would be 32. So our N value for SO3 would be 32. Now, the next thing we're going to look at is A. A would be the total number of electrons available. So A stands for how many electrons are available. And that actually is going to stand for our number of valence electrons, because those are the electrons involved in bonding in the outside world, are valence electrons. Now, if we have a polyatomic ion, we have to fix A, and that's something we'll look at a little bit later. So for a polyatomic ion, when you calculate your A, you have to subtract the charge. That's something we'll look at later. Now, if we have something like SO3 and we want to calculate its available valence electrons, we need to realize that sulfur and oxygen are different things, so we need to look them both up on the periodic table. Now remember, finding the number of valence electrons is really just counting across the S&P block, or looking at the group A group numbers up top. So sulfur, if you look, it's the 4th one over in our P block, so that would be the 6th over across the S&P block. So as you count across the S&P, you get to 6. So sulfur, and there's only 1 sulfur, has 6 electrons available. Now we also have 3 oxygens. So we got 1 sulfur and we got 3 oxygens. So we're going to put a 1 here and a 3 here. Sulfur, we just said, has 6 available. And if you look at oxygen, it's in the same column that sulfur is. So it also has 6 available. So what we really have here is 6 plus 18, total of 24. So in SO3, we need 32 electrons, but we only have 24 electrons available. And that's where S comes in. S is how many electrons must be shared. So it stands for the number of shared electrons. Now, 32 minus 24, N minus A equals S, would tell us how many shared electrons we have. So if we only have 24 and we need 32, that means we have 8 electrons being shared between the 2 atoms. Now, the last thing would be the number of bonds, and since a bond is a pair of electrons being shared, if you know the number of electrons being shared, divide it by 2, and you have the number of bonds, which in this case, 8 divided by 2, when we draw SO4 or SO3, we need to have 4 bonds inside our molecule. So this is basically the starting point for all of our octet substances. Anything that follows the octet rule, you use N-A equals S to establish how many electrons are being shared, divide that by 2 to find out how many bonds you've got. Now, the next step in the process, once we know the number of bonds, is we draw the molecule without the bonds. So first we're going to draw the central atom or atoms. If we had something like 2 carbons that would go in the middle, we just draw both of them side by side. Otherwise, we're just going to have 1 in the middle. Now, what goes in the middle? Well, in almost every case, this is the important idea. Whatever you have 1 is, that's going to go in the middle. Now, if you're not sure, you can look at what's least electronegative. So outside of hydrogens or halogens, so if you have hydrogen, it only needs 2 electrons to become stable. It's going to share once, it's done. It can never be in the middle. Halogens are the same. So fluorine, chlorine, bromide, and iodine, they have 6 or 7 dots. They're in 7A. So they have 7 valence electrons. If they share once to make a single bond, then they're going to have a full octet and they're going to be done. So with the molecules that we're looking at, hydrogen and the halogens will never be in the middle. So the least electronegative outside of those is what goes in the middle. And you never have to worry about that because you're really just putting the one there's only one of in the middle. All the other atoms you just space around the central atoms. So in the case of something like SO3, there's only one sulfur, so I'm going to put sulfur in the middle. Now if I wasn't sure, I could look up the electronegativities and you'd see that sulfur is lower, so you'd put that in the middle. And then you just space the oxygens out around it. So that's step 2, draw the molecule without the bonds. Step 3, we're going to put steps 1 and 2 together. First of all, everything has to be connected to the central atom. So we're going to draw single bonds between all of our outside atoms in the central atom. And if there's any left over, that's how we know we've got a multiple bonding situation. Now, if we have multiple bonds, they're typically going to go with the oxygen. I mean, they could go to other things, but most of the time with the molecules we're looking at, your multiple bonds are going to be to oxygens, or they're going to be involved with the carbon, because carbons also often have multiple bonds. Now, if you have something like SO3, remember from step 1, SO3 had 4 bonds. Step 2, we drew it without, and we ended up with this. Well, first in step 3, we're going to connect them all with a single bond. That gives us that structure. But we have 4 bonds, so we have to put that 4th bond somewhere else. Now, I talked up here about where it typically goes, but honestly you almost never have to worry about that. When you have a multiple bond, you rarely ever have a choice. Remember, it can't go to hydrogen or halogens because those are single bond, one and done. So it's going to go to something that isn't one of those, and that usually means we don't have a choice about where to put it. It has to go in one spot, or like in this case, every one of these is just an S to an O, so they're really, for all intents and purposes, the exact same. So we're just going to pick one and put it there since all of them are the exact same. So that's step 3. Draw until you've used up all your bonds calculated in step 1. If after single bonds you have extra, you're going to end up with multiple bonds like in sulfur trioxide. Step 4, you fill in dots to give everything a full octet. Remember, everything is supposed to have a full octet. Now the key to this step is, remember, you always draw your electrons in pairs. We typically talk about how many electron pairs you've got. So you don't draw singleton electrons, you always draw them in pairs. So in the case of something like HCl, N minus A equals S would tell us we have one bond, so we connect the H to the Cl with a single bond, and at that point we're done with bonds. But right now, the chlorine does not have a full octet. This bond represents 2 electrons. So remember, a bond is always 2 electrons. So right now chlorine has 2, it needs a total of 8. That means we need to draw 6 more electrons. Now remember, we always draw them in pairs, so a better way to think of it is we need to put 3 pairs of electrons around the Cl. Now bonds and our pairs that we're going to draw in now, they're all negatively charged. So the rule is just space them out. So keep the electrons together in pairs and then space them out. So I've got electrons here in that bond, so I'm going to draw my first dots across from it. Just space them out. That's as far apart as they can get because they're going to repel each other. But I have 2 more pairs I need to draw in, and those are going to go on the other 2 sides. Now at this point, my chlorine has 8 electrons. It's got a full octet. Do I need to put any electrons around the hydrogen? Well, remember, hydrogen is full when it has 2. That bond represents 2, so we don't put any dots on the hydrogen. So step 4 is basically to add electron pairs until everything has a full octet. Now, step 5 only applies when we have a polyatomic ion. If you've got a group of atoms with a charge, they're covalently bonded, so we can use N minus A equals S to predict what they're going to look like. But when you go and do the N minus A equals S and draw it, there's no way for somebody in looking at the picture to know we're talking about an ion. So what you do is, if we're drawing NH4 or NH4 plus ammonium, it would predict 4 bonds using N minus A equals S. So we would draw the nitrogen in the middle with 4 bonds stuck to it. But the only way to know that this is a cation with a +1 charge is if we show somebody that it is. So we put the whole thing in brackets, meaning this entire structure, and then we put charge outside the brackets to show what the charge is. So remember, if you have a polyatomic ion, Not only does it affect A, which we'll look at in a second, but we have to put the whole thing in brackets with a charge. Now let's look at a couple of examples here. So if we want to do NH3, NH3, remember, N is 8s and 2s. In NH3, we have 1 non-hydrogen and 3 hydrogens. So we're going to have a total of 14 for our N value. Now next would be available. Now we have 1 nitrogen and 3 hydrogens. When you look up hydrogen, you'll see that it has 5 dots. And when you look up nitrogen, it has 5. And when you look up hydrogen, it only has 1. So we have 1 thing that has 5 available and 3 things that have 1 available for a total of 8. Now how many we're sharing would be the difference between these two. So 14 minus 8. That means we have to be sharing 6 electrons. And remember, a bond is 2 electrons, so 6 divided by 2 gives us our number of bonds, 3. Now when we go to draw this, we're going to put our nitrogen in the middle and then just space out the hydrogens. Next we connect them with a single bond. That used all 3, so I don't have any multiple bonding here, which would make sense. Hydrogen can't have more than a bond anyway. But the last step, step 4, since this is not a polyatomic ion, would be to add our dots. All of the hydrogens are good because they only need 2 and the bond gives them 2, but the nitrogen needs 1 pair. So that would be our structure for NH3. Now if we're going to do oxygen, basically go through the same process. Remember, we want to figure out how many 8s and how many 2s to get our N value. Well, since we have 0 hydrogens, there's no 2s. And since we have 2 non-hydrogens, we've got a total of 2 there, which gives us a total of 16 needed. So O2, we have 16 needed. Now available for oxygen. Oxygen is in 6A. It's got 6 dots. So 2 of them means we've got 12 available, which means we're going to share 4, and we have 2 bonds. So when we draw our O's, doesn't matter where we put them, 2 things are always going to be next to each other. So we don't worry about a central atom in this case like we did with NH3. First we connect them with a single bond, but remember, we needed 2 bonds, so that means I have to put another one here. Now every bond is 2 electrons, so right now each oxygen has 4 electrons, so they need 4 more, which would be 2 pairs. And notice I've kind of spaced them out. I've got 3 things about as far apart as I can get them is that triangle 180 or 120 degrees that you see here. So that's O2. Next one, HCN. How many need 8? Well, we've got 2 of them that need 8. And we have 1 hydrogen, so we have 1 thing that needs 2. Well, that's a total of 18 of electrons needed. Now in our available, we've got a hydrogen which has 1, we've got a carbon which has 4, and a nitrogen which has 5. So we have a total of 10 available, which means we're sharing 8 and have 4 bonds. Now you'll notice how this one is drawn. It's drawn in a very, very specific way here. Carbon is in the middle. That's because carbon's always in the middle if it's there. And it turns out it's least electronegative, so I put that in the middle, and I would space out the other things around it. First, I would connect them with a single bond, but I have a total of 4 bonds, and I've only drawn 2. So I have to put in 2 more bonds. Now, what you normally do is probably split them up, put 1 on each side, but remember, this is a hydrogen, and hydrogens can't have more than a bond, so that means both of our extra bonds have to be over here. And what we end up with is a structure that looks like this. Now last we put in our dots, the H is good because it's got 2. The carbon has 4 bonds, that's 8, so that's good. But the nitrogen has 3 bonds. That's a total of 6 electrons. We need 2 more. And remember, you space them out, so I put that pair as far apart as I can. So that would be HCN. Last one I want to look at here is one that has multiple centers. C2H4 has 2 center atoms, 2 carbons in the middle. Now first we would go through, we have 2 things that need 8, and we would have 4 things that need 2. So 16 plus 8, we've got a total of 24 electrons needed. Carbon has 4, so if we have 2 carbons, and they each have 4 available, that's a total of 8. And to that, we're going to add our hydrogens. Well, hydrogens have 1, and we've got 4 of them, so that's going to add 4 more. 8 plus 4 is 12. So that means we're going to be sharing 12, which means 6 bonds. Now, when you go to draw this, if carbons are there, they just go in the middle. So we're going to stick 2 carbons in, and everything else just gets spaced around. So I'm going to space out my 4 hydrogens here. And then you connect everything with a single bond. That takes 1, 2, 3, 4, 5. Well, I have to have 6. Remember, hydrogens can't have more than 1 bond, so it's got to go here. Now, in this particular molecule, you don't need any dots anywhere because each carbon has 4 bonds, which is 8, and each hydrogen has 1 bond, which is 2. It's all good. Now, if you have a polyatomic ion, they're covalently bonded, so we can use the same method, but they've gained or lost electrons to become stable. So we can use N minus A equals S, but the difference is we have to change A, because if we've gained or lost electrons, we have a different number of electrons available. The easy way to do this is find A like you did before, and then subtract the charge. Because let's say it was 17 and a -1 charge. 17 minus -1 is 18. It would accurately show -1 charge means we've picked up an electron. So if we want to draw something like NO2 minus, we start with the same process we did before. We need N, we need A, we need S. Well, I have 3 non-hydrogens, so that's going to give me a total of 24. 3 times 8 is 24 available. Nitrogen has 5 available. Each oxygen has 6. So 5 plus 12, that's going to give me 17 electrons. Now, before I figure out S, because 24 minus 17 is 7, 7 divided by 2, 3.5. 3.5 bonds, that doesn't make any sense. So when we go to do this substance, before we move on, we need to correct our A value. Since we have a -1 charge, that means we would take 17 minus the -1, and that would give us 18 electrons. Now 24 minus 18 would give us a total of 6 6, so we would end up with 3 bonds. So when we draw this, we would need 3 bonds. So when we go to draw this substance, we would draw a nitrogen with our oxygen spaced out. We would connect them with single bonds, but we need a 3rd bond here. Once again, there's no choice about where to put it because they're both the same here, so pick a side and put it there. The nitrogen would need 2 dots. This oxygen would need 6. This oxygen would need 4, and because it's a polyatomic ion, we put it in brackets, and then we give it a charge, in this case, -1. And that's where I'm going to stop this set of notes through polyatomics. So in my next set of notes, I'll pick up with ideas from where I left off here. So if you're needing help on the whole chapter, remember you need to move on to the next set of notes.